Hello, and welcome to today's discrete structures lesson. We're going to take a look at conversion of base 10 decimal numbers to binary numbers. There's two different ways we're going to look at. One is a more traditional approach taken by most math books, and you may be familiar with. And the other one is the approach taken in your book, which is more from a computer coding point of view and maybe a simpler algorithm. So we're going to take a look at both of those and see how they both do the same thing. And in the process, I'm going to remind you about the meaning of the div and mod commands. So here's our little introduction. Your text provides an algorithm. I wanted to compare that to what you typically learn in school. Maybe some of you learned it even earlier in school. I remember seeing this very early on, maybe even before junior high, just as an interesting thing to do, but never had to do it much until I got into computer stuff. But anyway, so we're going to convert the number. I've chosen to use the number 83 as our example. This is something that's probably best done by example. And what I wanted to remind you of is, first of all, what are the place values in base 2? So if I have a base 2 number, I have place values. If I start, I'm going to start from the right and move to the left and write in the place values here. And they're all powers of 2. And so this is going to be a base 2 number. So we'll write the 2 just indicate in binary. This is how many sets of 1, and then how many sets of 2. And then 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. And 64 times 2 is 128. We can stop there for now, but you keep going up as multiples of 2. Every time you move one digit to the left, you multiply its value by 2. In base 10, our values are a 1, a 10, 100, 1,000. We're multiplying by 10. Each time you move one digit to the left, you are multiplying by the base one more time. So what we want to know is in 83 in base 10, and notice when we don't write the base, it's assumed to be base 10. 83 in base 10, how do we turn that into its equivalent base 2 number? Well, most math books will start with you look at the number 83 and you look at the value of these places that I've written here. The 1, 2, 4, 8, 16, 32, 64, 128, and find the largest value that's smaller than 83. So 128 is larger than 83. 64 is smaller than 83. So the most types of things I can get is I can get one set of 64. I can't get any more than one set of 64 out of this. I can't get a whole set of 128. So I start with the 64. And what you do is you do this division process, and you probably don't even think of it this way. And when you're doing it base 2, you do 83 divided by 64, and you get a 1 with a remainder of 19. That 1 tells you how many sets of 64 you have. Then you take the remainder. So this 1 accounts for 64 of the 83. You take the remainder and you divide it by the next place value. 19 divided by 32 is, you can't take 32 out of 19. You can't get a whole set of 32 from 19, so it's a 0. And this would be the value of what you get when you do the div command, and the remainder is what you get when you do the mod command. But I would have 0 with a remainder of 19. And if I do 19 divided by, so I put the 0 here. Okay, divided by 32, I get div is 0. 19 divided by 16, I'm going to have 1. I can take a whole set of 16 out of 19, and I would have 3 left that didn't fit into that set of 16. So I put a 1 set of 16. So I'm putting the values of the div into the places, and I'm moving left to right. So I take 3 and I divide it by 8. I can't get any sets of 8 out of 3. No, there are no sets of 8 in 3, so I still have a 0 and I have a remainder 3. I'm going to find the same thing. If I do 3 divided by 4, I cannot get I have no whole number quotient. 0, remainder 3. Then if I do 3 divided by 2, I do get 1 with a remainder of 1. So I put a 2. And then if I do 1 divided by 1, I get a 1 with a remainder of 0. So I'm at 0. I have nothing left to convert. So what you see is when I do it in this method, my result comes moving left to right from the values of the quotient. So these are all, so if I read these left to right, 1, 0, 1, 0, 0, 1, 1. I went from left to right. Now the algorithm of your book does this a little bit differently. Let's take a look at that. I'm going to use the same number for the example. So here is the algorithm from your text. 1.4.2 is the section it comes from. An algorithm for determining the binary representation of a positive integer. And we're going to work through the number 83 in this. Now look, your input is a positive integer. For us, that's our number 83. Our output should be what we just got when we converted to binary. We should get the same thing. But watch how this does it. Remember before we were taking the quotient part and we had to figure out where to start to begin with. And this time, first you're going to initialize an empty list. And you're going to take a value k and define it as your input number at the beginning. So in the beginning, k is going to be 83. So when I do the first, I'm going to do this step over and over again while k is positive. When you see this greater than 0, think is positive. This is what I'm going to do. I'm going to do k divided by 2. So you're dividing by the base. Notice you didn't have to figure out, oh, I need to start with 64. All you need to know is the base. You know that. It's 2. So in the first iteration, I take 83 and I divide it by 2. So the k div 2 gives you, so q is the quotient value. And when you take 83 and you divide it by 2, you get 41 for the quotient, and you get a remainder of 1. Now, when you divide a number by 2, there are only 2 possibilities for a remainder. You get a 1 or you get a 0. That's part of what makes this work. And this works well for bases beyond 2. This is a more generic conversion. You would divide by 3 if you want to do base 3. But for now, what I do is I take the remainder and I make that the first. I write that, they say add that to the front of L. So here's my list L. I don't remember how many digits I needed, but I add it to the front. Well, right now the front really is prepend it, so I would put it here. But every time I add a number, I'm going to move it down. So maybe I was premature in writing all those spaces, but I'm going to put a 1 there. And all the rest of these are zeros or empty. Okay, they're actually empty. Then so I've done this step here. Q is 41. I don't do anything with that. R was the 1. That's what I use, and then I put that R in the leftmost space of L. So now I reassign k is what the quotient was. That's where the quotient gets used. So now I have 41. And I can do that same process. I'm going to divide 41 by 2. Now, when I divided 83 by 2, the quotient told me how many sets of 2 there were and how many were left over. Well, when you have a leftover from a set of 2, that must be your units digit, because anything that's not even in binary will have a 1 in the units digit. So when you divide by 2 and you get a remainder, that goes in the next digit. Now, when you divide by the 41 by 2, what you're really doing is finding out how many sets of 4 there are in what's left. So I've got 41 sets of 2. So the question is, how many sets of 4 can I make out of those sets of 2? So when I do that, I get my quotient is 41 divided by 2 would be 20, with a remainder of 1. So again, my k div 2 will be 20. My k mod 2 will be 1. And I have another 1. So now I have 2 1s. I actually move this 1 to the right and put a 1 in front. That's what I'm doing with the prepend. This is kind of a pseudocode. They do this in Sage in your book, but this gives you a pretty good idea of how this would work. So now I again reassign Q to be the quotient, K to be the quotient rather, and I divide that by 2. And I get my new Q is 10, and my remainder is 0. So I put a 0 out in front of so these are the 2 1s here. That 0 goes in front. It gets appended to the left. Now I do 10 divided by 2, and I get my quotient is a 5. Now, when I did 83 divided by 2, I got the quotient was how many sets of 2 there are. Then I take that and divide by 2, that's how many sets of 4 there are. I take that and divide by 2, that's how many sets of 8 there are. And I take that quotient and divide by 2, that's how many sets of 16 there are. So there's 5 sets of 16 basically is what that's telling me. And when I divide 10 by 2, I get a remainder of 0. So now I have, this next step becomes 0, 0, 1, 1. I take the 5 and I divide it by 2. I get a quotient of 2 with a remainder of 1. So now I have 1, 0, 0, 1, 1. That one goes down there. And then when I take the quotient of 2 and divide it by 2, I get a 1 with a remainder of 0. So I get another 0. Let me move this down a little. 0, 1, 0, 0, 1, 1. That one goes there. And then when I take the quotient of 1 and I divide by 2, I get a 0. So now my Q is not greater than 0 here. Note, when we go back to the code, notice it was not greater than or equal to 0. It was while K is greater than 0. So when I reassign in this last step, when I make K equal to 0, that's going to tell my loop to stop. So I get no sets of 2 can come out of 1, and I get a remainder of 1. That 1 again goes in the front. So I have 1, 0, 1, 0, 0, 1, 1. That is my base 2 equivalent for 83. And just as a reminder of how to convert back and check, I have one set of 1 plus a set of 2, so that's 3. 4, 8, 16 will be 19. 32 is none of them. 64 plus 19 is indeed 83. So that's how I could check my work. And if you looked at the earlier part of the example, you would see we got the same answer. So this algorithm works by taking the remainders and moving from right to left, essentially. In the first algorithm we took the quotients and moved from left to right. Thought that was interesting to take a look at from a coding perspective and from a number sense perspective. I hope this helps explain this to you in a way you can understand it better. Email me your questions. Thank you.